Hello class, this is lesson 3.4, integer word problems. Well, we finally arrived at the word problems, where everything that I did in Unit 2, Unit 3, and even parts of Unit 1 were really to build to the point where you could take a sentence and solve the question. And that's really the point of math, is that you can actually apply it to real life. Just as a reminder, all the different things you learn can be encompassed nicely in this flowchart. But of course, all we're doing right now is we're going from the word problem to standard form. That is it. I mean, within the questions, I'll sort of show you what the answer looks like. And typically today, I'm going to go from the word problems to standard form. And then I'm just going to use the quadratic formula every time. There's other options to do different things, but for today, that's what we're doing. So let's get to it. Quick thing about word problems is that when someone shows you the answers, it can look remarkably similar. It can look remarkably simple because you're seeing the answer and then you're like, oh, that makes sense. I get that. I could do that. But when you have a blank page in front of you, it's actually a much harder thing to do. So don't trick yourself into thinking that you've got this when you don't, because the truth is that it's something that you often need to struggle through, and that's really hard for me to replicate in this kind of environment. The best I can do is just kind of block the answers here and ask you the questions and then move forward that way. So today's word problem is an integer word problem. That's basically me saying to you, this kind of word problem is about missing numbers. So in the first question, before we get to that, with all the questions that you do, you're going to have a let statement. You're going to make an equation in standard form, you're going to solve it, and then you're going to have a concluding statement. Because they're word problems, you need to set them up and close them properly now. The first question is a consecutive, even odd type question. So here we go. The sum of the squares of two consecutive positive integers is 481. Find the integers. We say the word integers, we just basically mean missing numbers. So, the sum of the squares, and of course in real life we would never speak like this, but in math talk you need to be able to deconstruct it. And if you paid attention or participated in lesson 3.3, you should know that this is an addition. Squares, that's a new one, but that just basically means everything's going to be squared. Consecutive, that word means one after another. So when numbers are consecutive, if we have the number 11, the next consecutive number is 12, and so on. And when we say is, we're really describing an equal sign. So the first thing you should do with any word problem is probably do these kinds of markings. Give yourself some clues. The next thing you should do is state your let statements. In this case, and often, x is just going to be our missing number. And our first number is usually going to be x. Well, we know there's a second number. There's two numbers. And if the first number is x, and the next number is just one bigger than x because it's consecutive, then we know that this has to be the second number. This is a really key piece right here. Again, if, for example, I said the first number is 14, then you know our second number is 15. Or if it was 23, our next number is 24. The next number is always going to be one bigger than that first number, which is why we have x plus 1. Now we know these two numbers are going to be added together and squared, and that's going to equal 481. So pull down slightly, and here we are. Here's our first number, here's our second number, there's the sum of them, and this is them each being squared, and they equal 481. Going from this to this might look simple. It can be really difficult if you don't have the practice, because this isn't normally how we ask about missing questions in life. But once you've learned sort of what the words mean, it should be pretty easy. At this point, you are now required to put this into standard form. So let's square this. Remember that what this is this square here really means there's two binomials. We've gone over that before. When we multiply it all out through foiling, this is what we get. And what I've just boxed off here is the standard form equation. We've now put everything onto one side of the equation. Here's our a value, our b value, and our c value. And now we have it all set up. And once you can get from here to here, that's definitely the hardest part. Because it should be at this point pretty easy, follow my arrow, to now do the quadratic formula and solve for the answer. Now in this case, we're going to get two answers. One says that x is 15 and another says x is negative 16. Well, because we did the quadratic formula, we're often going to get two answers. In this particular question, it says consecutive positive integers. This is a negative integer. So therefore, our first number is 15 and our second number is one bigger than 15, so our second number is 16. Okay? That's one of three questions in this lesson. Let's try another one. Find two integers whose sum is 96 and whose product is 1728. So there's actually two different ideas here. First off, let statements. Let's make the first number x, and we don't know what the second number is. We can call it y. Now, if you're a little bit stronger in math, you might recognize and say, wait a second, shouldn't the second number just be 96 minus x? And if you get why that happens, congratulations, you're a step ahead. If you don't understand why that happens, it's okay, we're going to get there. So again, if you have two numbers and you don't know what the two numbers are, one's x, one's y. So follow me right here. The sum of our two missing numbers is 96. And our product, multiplication of our two numbers, is 1728. So we have 1 and 2, different equations. This is a linear system, which we'll want to solve for x and y. And what we can do is substitution. So this equation here can be rearranged. I'm basically taking that x and moving it to the other side so that now y is equal to 96 minus x. See these pink brackets? That's what y is. This is substitution. Y is this. Well, I see a y down here. I don't have to write y anymore. Pink brackets again. I can rewrite y as what it is. This method, this part of solving for this question can be skipped if you automatically understand that the second number can be represented as 96 minus x. And if you don't, well, do this and you'll get to the same place, just a little bit more work. Okay, so let's put this in standard form. I'm gonna distribute that. Oh, follow the arrow. And move everything to one side of the equation. I chose to move everything to the right side of the equation. So that negative x became a positive x. But I could have just as easily moved everything to the left side and had a negative x. It doesn't matter. At this point, we're gonna solve. And we're going to get two answers. Now, these two answers are going to be x is 24 and 72. Well, how could x be two different numbers? Well, the reason is that if x is 24, then the y has to be 72, because they both add up to 96. Or if x is 72, then y has to be 24. Well, we arbitrarily decided which one was x and y. First, it doesn't matter. So it's either this or it's this. It doesn't matter. What really matters is that, I should have a therefore statement here, is that therefore the two numbers are 24 and 72. That's the answer to this question. One last one. Hypotenuse question. The hypotenuse of a right triangle is 20 centimeters. The sum of the other two sides is 28 centimeters. Find the lengths of the other two sides. So let's make x the first side and y the second side, because those are the two lengths that we're looking for. And again, let statements are always, what is it that you're looking for? So if I add up these two sides, it should add up to 28. Oh, that's easy. Okay. Now, the second equation to create this is maybe not as obvious, but the Pythagorean theorem is what we're going to use. So that the square of one side plus the square of the other side equals the hypotenuse squared. So for a hypotenuse type question, you're just going to have to know Pythagorean theorem plays in somehow. And that's, again, through practice. By doing this question, now you know when you see that in any word problem that I provide you that Pythagoras' theorem is a part of it. Again, we're going to do substitution. Y is 28 minus x. there it is. Follow the pink brackets. That's what y is. Well, I just rewrote it here with y being what it is. I'm going to FOIL that. Bunch of work. Oops. And there's my standard form equation. Again, I'm going to use the quadratic formula. I skipped that entirely because I don't really have room here on this question. Maybe I didn't provide you enough room. My apologies. And we're going to get an answer of 12 and 16. Well, which is it? I don't know. I mean, it's arbitrary. Which one is 12 and which one's 16? It's 12 and 16 like this, or 16 and 12 like this. Either way, the side lengths are 12 and 16. So those three questions that I just went through with you are mirrored very, very nicely in the homework here. I'll let you know which ones are the homework questions. And again, if you're stuck on any of the homework questions, come back to these questions that I just did with you, because all these three represent the homework that I have in there for you. And make sure you do this, because we got something very new or completely different the next go around with different kinds of word problems. Okay, so that's about it for today's special feature. I have my favorite coin. This may not surprise you. I'm a coin collector. Have been my whole life, and my favorite coin is this American silver dollar. And if you can see it, it says it right down there. It's from 1884. This is 136 years old, this coin. Made of real silver, because a long time ago people believed that the money that they trade amongst each other should be actually made of something valuable. Money no longer is made of anything valuable. It's made of steel, plated with something. If you're wondering why that is, oh, that's a whole other conversation. But yeah, that's my favorite coin. So if you like that, I've got lots more coins to show you.